Alright, welcome to Analog Electronic Systems. So, let us continue where we left off. So far we have seen operational amplifiers, uh, and VO we said was A times V1 minus V2, where A tended to infinity, right. And we also saw some practical non-idealities, namely offset and saturation. All right. Of course, finite gain, I mean, finite gain meaning that the gain A only tends to infinity, it is not actually infinite. Again, depending on the kind of op amp that you buy in the market, typically off the shelf op amps have gains of the order of 10 power 6 to 10 power 7, and that number will vary over temperature, right. So, it is not like the gain remains constant over all temperatures and so on. But we know that this should not bother us, because as long as the loop gain is sufficiently large, how large it is of not really much consequence. So, circuits must be designed so that the feedback factor is such that number A times F is sufficiently large over all temperatures and all operating conditions. Okay. Now, but this still assumes that the op amp is infinitely fast. Okay. So, that basically means that if V1 minus V2 changes suddenly, the implication of this equation VO is A times V1 minus V2 is that if V1 minus V2 changes suddenly, then VO also changes suddenly. Okay. And that is basically I mean, that is of course non physical, right, because nothing in the world can change suddenly, right. So, it turns out that the actual model for the will going forward we will figure out why it is like this, but it just so turns out that it is VO of S by V1 of S minus V2 of S is not, ideally we expected it to be A, where that A tended to infinity. It turns out that it is not. It basically has some frequency dependence, as you can imagine, and it turns out to be of the form A naught over 1 plus S over omega, right. So, A naught of course represents the finite DC gain, and omega D represents the what is called the dominant pole frequency. Okay. So, if you draw the Bode plot for the magnitude response, so this is also log plot. Then what can we say? Well, for frequencies less than omega naught, we have omega D rather. We have the magnitude being 20 log A naught. Okay. And Beyond that, the gain falls off as minus 20 dB per decade. All right. So, for omega much greater than omega d, this transfer function, which is a naught by 1 plus s over omega d, is approximately, can be approximated as, pardon? Very good, a naught times omega d over s, right. And of course, the true a naught omega d by s would basically go off to infinity along that line, right. But you know, in practice below omega d, the gain cannot become infinite, it's some finite large number. And so, what comment can we make about that frequency there? I mean, so this is 0 dB. So, what you know, what comment can we make about that frequency? It is. So, basically, so the frequency response, so magnitude response is simply a naught omega d by s evaluated at s is equal to j omega, and we take the magnitude of this, and that is nothing but a naught omega d over omega. And the magnitude response is 1 when omega equal to a naught omega d. So, 1 is unity. So, basically this is called the unity gain band, right, of the opamp, and is given by a naught omega d. All right, and remember that a naught omega d is therefore called the unity gain bandwidth. There is another name for this. A naught represents the gain, and then omega d represents the 3 dB bandwidth. So, this is often also called the gain bandwidth product of the opamp. All right, and please remember that omega d is in radians per second, right. It's not it's not in hertz. Omega d is in radians per second. Is that clear? Okay. Now, now with this, you know, with this non-ideality there, let's go take a look at, you know, some common circuits and see what the effect of gain bandwidth is on the performance of these circuits. So, for example, okay, so now I mean the opamp, if the opamp was infinitely fast, then V naught by Vi would have been exactly k, right, which also indicates that then the closed loop, I mean because the open loop amplifier is infinitely fast, it just so turns out that the closed loop one is also infinitely fast, right. But in reality now the op amp has got some speed limitation, which therefore means that the closed loop amplifier will also have some speed limitation, right. So, so let us see what happens. So, how would we go and analyze this? Well, it is a straightforward circuit analysis. So, this is what comment can we make about that voltage there? It is still V naught by K, and so therefore, V I minus V O by K multiplied by, yeah, mean A naught by 1 plus so this is this is often also gain bandwidth product is also called GB, also called omega u. Omega sub u basically stands for unity gain frequency, GB stands for gain bandwidth product. So, so the transfer function of the op amp can be approximated if the DC gain is sufficiently high, then this is approximately omega u by S, correct. So, V I minus V naught by K times omega u by S equals V. So, V I minus V naught by K must be equal to S over omega u times V naught, which therefore means that V naught by V I, the transfer function between the input and output, is given by yeah, can you arrange that properly? So that the denominator, the constant, I mean you should always arrange transfer function so that the constant term in the denominator is always 1. K by 1 plus Sk over omega. All right. So, as expected, at DC, what is the gain? And is that surprising? Yes or no? Why does that make sense? It's infinite, okay. So, therefore, virtual short is valid. So, therefore, Vi basically must be the same as Vo by K, which basically means that Vo is K times Vi. Now, the important question is, is this virtual short concept now valid at all frequencies or it's only valid at DC? It's only valid at DC. Why? It's only at DC that the gain is infinite. As the frequency keeps increasing, the gain actually is no longer infinite, it keeps falling off. So, therefore, I mean, why did we say that the virtual short concept holds when the in the earlier case we said that if the output is finite and if the gain of the amplifier is infinite, then the input difference between the two terminals at the input of the op amp must be 0, so that we have a you have a finite output, and if you have infinite gain, the difference at the input of the op amp must be 0. In this case, it only happens that infinite gain only happens at DC. Therefore, it follows that this is only true at DC, and it's not true at other frequencies. Is that clear? All right. So, so at DC, of course, since the gain is infinite, VO by VI is simply K. What is the 3 dB bandwidth of the closed loop amplifier? It's nothing but omega u over. All right. Okay. So in this amplifier, so closed loop DC gain times the closed loop 3 dB bandwidth is what? K times omega u by K, which is, right. So the key point is in this amplifier, it just so turns out that the product of the DC gain times the 3 dB bandwidth just so happens to be the same as the unity gain bandwidth of the op amp. All right. So, but now once people see this, they somehow mistake that this is true for all amplifiers, and that's not true. Okay. All right. Let me show you. So, by the way, I mean, so if you increase the closed loop DC gain, if you want a higher closed loop DC gain, then the bandwidth reduces. All right, let me take another example. Let us now take the non-inverting amplifier or the inverting amplifier. What is VO by VI? Minus K. All right. And so now, how will we? What is this voltage at when the op amp is ideal? Now, of course, when the op amp is not ideal, this transfer function is omega u by S, and that is nothing but what is that voltage? Yes, Nandita. V naught. Why? What is this voltage in terms of? You have two resistors, one end is connected to Vi, the other end is connected to V naught. What is the voltage in the middle? Yes, Praneeth. V naught Okay, so V naught times 1 plus Vi times k by k plus 1, right. So, this multiplied by minus omega u over s must be equal to V naught. So, V naught times omega s over omega u plus one over k plus 1 must be equal to minus Vi to k over k plus 1. Okay. So, Vo by Vi is nothing but minus k over 1 plus s times k plus 1 over omega. That clear? Now, what is the DC gain? Is minus k. The bandwidth omega u over k plus 1. Okay. Right. So, what is the, so here is an example when you multiply the gain with a 3 dB bandwidth, what is the product? It's basically if you multiply the magnitude of the gain with the bandwidth, you no longer get omega u, it's omega u, something close to omega u, but it's not omega u, right. So, definitely gain times bandwidth is not a constant, not the same as not constant and not equal to omega u.